Hello, this is MATH1081 and this is the last video for Chapter 1, and in this video I'm going to go through and just do solutions to one of the sample tests at the end of the chapter. So we're going to look at an old class test. This is from 2008, Session 1, Test 1, Version 1A. And there are 3 questions there and I will go through and solve each one of them. So the first one says, I want to show that this set, now the question doesn't actually give it a name, so I'm going to change it a little bit and I'm going to call that set S and give it a name. That makes it easier to describe or to talk about. And I want to show that is a proper subset of this set, which also is not given a name, and so I'll call that one T. And so when you're doing this, if you're doing this in a class test, I would have written down the 2 sets and actually give them some names. Now I want to show it's a subset, and I want to show also, note the language here, a proper subset. So I might do that bit first. So we might just simply note that S and T are different. S does not equal T, since I want to find some number that belongs to this set that doesn't belong to this set. Because this one lives inside that one, but it's a proper subset, so I want something in here that doesn't belong to there. Well, start putting in some numbers for M. I could put in 1 and I get -3, and that would be okay, but probably safer to put, say, M equals 2 in, and so I'd get 2 there. So for example, 2 belongs to T, but 2 does not belong to S, because you can't take a multiple of 10, add 7 and get the number 2. So the 2 sets are not equal, and when I finish proving it's a subset, that will show it's a proper subset. Now to show this is a subset of that, we must take any element of here and show it also belongs to there. So we start off with suppose X belongs to S. So I take any old object in this set S. Then I have to write down, how did it get there? How did this number X get into the set S? Well, it got there because it must have been a multiple of 10 plus 7, and some important English here, for some integer k. Very important to put the English there. X doesn't equal this for any general k, it's for some particular integer k. Okay, so X is equal to then 10k plus 7. And to show it's in T, I need to show, and again put it into English, I need to show it's a multiple of 5 minus 8. So it's 5 times something minus 8. So I have to rewrite this and write this as 5 times something minus 8. And now I just stare at the equations and see what can I put in the brackets that will make these 2 equal. Well, I've got a 10k, I need a 5 times a 2k to get me the 10k. I need a 7, so I'm thinking 5 times something minus 8 is 7. Well, 5 3s are 15 minus 8 is 7. So now this number equals this number, and I've shown now it's a multiple of 5 minus 8. So I can write this as 5 times m minus 8, where m is 2k plus 3, is an integer. That again is important to write because this m had to be an integer, and it is because it's twice an integer plus 3. So that means my x then belongs to the set T. So I started off with an object in S, done something to it, and I've shown it also has the same shape as the numbers in T, and so X belongs to T. Conclusion, therefore S is a subset of T, and S is a proper subset of T, because we've shown the 2 sets were not equal right at the beginning. So that's the solution to the first question. Now, if you'll bear with me while I rub this bit out, and I'll put up quickly the second question, and then we'll solve that problem. So the second question is on functions. And the second question says, we take f, maps the A to B. I'll summarise that by writing f maps A to B, g maps B to C. These are functions, and we're asked to show that if the function g circle f is 1 to 1, we're asked to show that the function f is 1 to 1. Another name for 1 to 1 is injective, is the fancy name for 1 to 1. I like to draw a little picture. You don't need to do the problem, but I like to draw a little picture at this point just to visualise what's going on. There's the set A, there's the set B, there's the set C. F is taking me from A to B, and G is taking me from B to C. So when I take a number x over here and I want to map it across, then I have to firstly apply G and then apply F. So the composite map here is written as G circle F. As G circle F. Let me just check I've written the question correctly. Yep, that's G circle F there. So I'm given the fact that G circle F is 1 to 1, and I want to show that F is 1 to 1. 1 to 1, remember, means that if you start out with two objects and they map into the same thing, then in fact the two objects you start out with were in fact equal. So if I start out with an x and a y and I map them across, to show f is 1 to 1, I need to show that these x's and y's were in fact the same thing. Now whenever you're proving something is 1 to 1, the idea is you start out with the following statement. So you start off with suppose f of x equals f of y. That is, I start out with two numbers x and y, I apply f to them, I land here. Then I want to show, the name of the game is I want to show x equals y. So I'll just write that down here. We need to show that x and y were in fact the same in the first place. So that's what I'm given. I'm given G circle F is 1 to 1, and I want to show F is 1 to 1. So I start off with that statement and try and get x equals y. Now I've got to get G into the story somehow, because at the moment I've only got expressions involving F. And the easiest way to do that is simply to take G of both sides. So that's G of f of x is G of f of y. So I'm just applying the function g to both sides of my supposition. Again, look, undo the notation. G of f means G circle f of x. This is G circle f of y. And now remember, we're given that this function G circle f is 1 to 1. We know that one's 1 to 1. And that means whenever I apply this function to two different numbers, then the two numbers must have been in fact not different, they were in fact the same. And the reason for that is since G circle f is 1 to 1. So I've satisfied what needed to be done. I've started off with f of x equals f of y. I've shown that x is equal to y, and therefore we can conclude that f is 1 to 1 function. And that's the end of the problem. So that's question 2. Again, let me just clean this off, and then I'll put up question 3, and we'll have a look at the solution of question 3. So question 3 is from the last section of this chapter, and it's to do with series, with evaluating and manipulating finite series. Using essentially, in many of the examples, and we will here as well, using essentially a technique that you will have learnt in lectures. And let me just write the question up. So k is bigger than 1. The first part is easy. It says we want to show that 1 over k minus 1 squared minus 1 on k plus 1 squared is equal to 4k divided by k squared minus 1 all squared. So that's an easy bit of algebra. I would start off with just here's the solution, left-hand side equals, put it over a common denominator, and then I get k plus 1 squared minus k minus 1 squared. And now in the denominator, I've got k minus 1 times k plus 1, so that's difference of two squares, all squared. And on the top, well, you can sort of cheat at this point. You can just say, look, it's obviously equal to 4k, because you can do the expansion mentally. You get k squared minus k squared cancels, 1 minus 1 squared cancels. I get a 2k from there, minus 2k is 4k. You don't need to put all the, you can if you like, you don't need to put all the steps in, that's sufficient. Because what we're aiming to do now is to use this identity that we've just found to sum a series using this technique called telescoping series. And the question we're asked now to sum is the sum k over k squared minus 1 squared, and we're going from k from 2 up to k equals n. So we want a formula for this sum. Now, obviously we're going to be using the result of part 1, otherwise there wasn't much point to part 1. And we can see that the k on k squared minus 1 squared is there, but it's got a 4 there. So first step is to divide both sides by 4. So I'll put a big bracket in here, and this is going to be the sum 1 over k minus 1 squared. And this is k goes from 2 up to n. And I'm going to split that immediately. This is k is 2 up to n, 1 on k plus 1 squared, close bracket. So I use that, that's by part A. Now this is going to be an example of a telescoping series, and what that means is that if you were to write all the terms out, which is one way of doing this, I'm not going to do it that way, but you could write all the terms out, you'll see that the terms cancel with each other. All the terms in the middle cancel, and you're left with a few terms at the beginning and a few terms at the end, and all the rest telescopes in, hence the name. I'm going to do this, and there's nothing wrong with writing all the terms out and showing it cancels. I'm going to do it a slightly more sophisticated way here. In this problem, I'm going to make a change of variable in this second sum. I could change the first sum, it doesn't matter. I want to make this one look the same as that one. So what I want here, I don't want k plus 1. I really want it to look like k minus 1. So I'm going to put k plus 1 is j minus 1. I'm going to make a change of variable so that this will become a j minus 1 squared, which looks the same shape as that one. And I'm only going to make that change of variable in this sum. Now when I do that, let me just write this down then. So this is k is 2 to n. I'll leave this one alone. So here I have to check carefully. When k is equal to 2, I get 3 here. So j will be 4. And when k is equal to n, then I'm going to get j is n plus 2. So when you change the dummy variable here, you must change the endpoints as well. So the n becomes n plus 2, j becomes going from 4, and this becomes 1 over j minus 1 all squared, close bracket. So these now are looking the same shape. I've got to worry about the fact that this begins at 2, this begins at 4, and this finishes at n, and this finishes at n plus 2. So I'm going to take off the first couple of terms of this one. So put k equals 2 in, I get 1 over 1 squared. Put k equals 3 in, I get 1 over 2 squared. Then I'm going to get the sum k equals 4 up to n, 1 on k minus 1 squared. And then minus. Now I'm going to take the last couple of terms out of this one. So I'll put n plus 1 into here, which will give me 1 over n squared. and then I'll put n plus 2 in, which will give me n plus 1 squared. And then I'm going to have minus sum j equals 4 up to n 1 over j minus 1 all squared, close big bracket. Now at this point, these two series, this j and k are dummy variables, these are exactly the same series, so these two series cancel out. All the terms there cancel out one with the other, and I'm just left with a bit at the beginning and a bit at the end. So I end up with 1/4. Now this is 1 plus a quarter's 5/4, and then I've got minus 1 on n squared, minus 1 on n plus 1 all squared. I could simplify that at the end. It's probably best left as it is. You could put them over a common denominator, but I think I'll just leave it like that. But what we should do at the end on a scrap piece of paper or somewhere is just to check that the answer is reasonable without having to go through and double check all the calculations. And one easy way of doing that is to say, well, this sum goes from k from 2 up to n. Well, what if I put n equal to 2? Then the left-hand side, if I put 2 in here, I would get 2 over 2 squared's 4 minus 1, so I get 2 over 9. It's 4, yep, 2 over 9 from there. And the right-hand side, I can squeeze it in here, will equal 1/4 into, I get 5/4 minus 1/4 minus 2 plus 1 is 3, I get 1/9. And when you simplify that, it does in fact equal 2/9. So tick, it looks like it's working for at least n equals 2, so I've got a good chance that I haven't made any mistake in the calculation. So there's the solution of the sample test.